Okay, hello everybody. Um, this is our lecture, the next lecture. So this will be the material for the lecture that we missed on Friday, right? So let me just share the slides. Okay. Okay. So we go to the first slide. Select 25, and let's just go through this, and I'll explain the content. So some of this we saw last time. Some of this we saw last time. Um, like distributional complexity is something we are already familiar with. It is given a probability distribution mu over the inputs. The distributional complexity is the of a function is the cost of the best deterministic protocol that gives the correct answer on at least 1 minus epsilon fraction of the inputs. So the subscript of d is the error allowed, and the superscript mu is the distribution, right? The other thing, the bullet points are just explaining the definition. We have gone through this last time and before that as well, right? And the next slide, we saw this theorem. We proved this theorem that the randomized, the public, the randomized complexity with public randomness for a function f is the max over all distributional complexity. The max is taken where the max is taken on all the distributions. So the point is that this can be used as a lower bound technique for the randomized complexity, right? So now we can for we can pick one distribution for which we can take one distribution mu for which the distributional complexity is large. Now that becomes a lower bound for the randomized complexity as well, right? Yeah. Okay. Again, we have seen this in the previous classes. Okay. Now that that is out of the way, let me just uh, give you a summary of the way I want to go ahead. Like this, pre-recorded videos will be sent to you, and I would want you to go through this and before the discussion sessions. I understand this particular video is coming a bit late, so you may not get that much time. But I would like you to go through the pre-recorded videos and come prepared with questions, right? And during the regular class meeting times, we will have discussion sessions. Um, and I will also prepare one more homework assignment in addition to the one that you have already done. It. We will have one exam and a presentation, and I will soon share the list of topics that you can use for that you can prepare for the presentations. Okay, so this is a rough plan for the semester, and there are three final year students, and I will communicate to them separately what the expectation is. This is for the non final year students. The exam will be held in July as per the revised schedule, and the presentation also will be held in July. But you will have ample time for reading and preparing the presentation topics. And this is the rough idea of the topics I thought we could cover in the rest of the semester. So one is discrepancy related bounds, so which I have prepared for this lecture today. Let's see how far we go ahead. Right? This we'll define discrepancy, and we will see how discrepancy can be used as a way to get bounds for the randomized communication complexity. And this very technique is going to be used for randomized complexity of disjointness. We'll exhibit a distribution for which the distributional complexity is at least square root n. In fact, the randomized complexity for disjointness is actually at least n is linear, not square root n. But I'm not sure whether we will have time for that. So we'll see if we get time, we can cover that. I'm not sure at this point. Especially, I'm not sure at this point. Then we will see the one-way communication complexity of disjointness, where only one-way communication is allowed. And this will also, we will also see some applications in streaming algorithms for the one-way complexity, right? And one such application is that the zeroth moment. Okay, I think when Karthik took the lecture on streaming, the zeroth moment requires at least 1 by epsilon squared space, right? So this result will you make use of the one-way complexity of disjointness. And yeah, so this is the rough set of things I wanted to cover in the lectures that we have left, and maybe one or two more topics if we have time remaining. And if we had the semester ongoing in the normal course, we might have had presentations in the last 2 weeks or 2 weeks, for instance. So because of that, I may teach a few less lectures than what is mentioned in the calendar, because the rest of the time I just want you to read your papers and prepare for it. And of course, you could always contact me and ask questions for the topics that have been already covered, or the presentation topic that you have chosen. Okay. Anyway, the details of the presentation topics I will share with you separately. Okay. So discrepancy, we briefly saw it last class. So the idea is, remember we had a size bound for disjointness. That is, any one rectangle has size at most 2 power n, and we saw that there are at least there are exactly 3 power n 1 entries. So there has to be at least 3 by 2 power n 1 rectangles in any protocol. That gives you a linear bound on the deterministic communication complexity. Instead, discrepancy, what it does is it tries to show bounds. So here we are talking about, in the size bound we had limited the size of monochromatic rectangles. In discrepancy, we will limit the size of almost monochromatic rectangles. Okay. So given a function, a 0-1 function, the discrepancy of a rectangle, of a combinatorial rectangle, is the number of zeros minus number of ones, the absolute value of that. Okay, not number of zeros, but the measure of zeros minus measure of ones, the absolute value of that. So the measure as per the distribution. Okay, so this is the discrepancy of the function of a rectangle of the function with respect to distribution mu, and the discrepancy of the function is the discrepancy of the rectangle R, which maximizes this, right? And so if a discrepancy is small, then that means the discrepancy is chosen for the discrepancy of the function is taken to be the maximum over all the rectangles. So the discrepancy is small, then all the rectangles must have small discrepancy, and hence all the rectangles must be balanced. Meaning, so one way to think about this is that don't think about strange distributions. Just think about the uniform distribution, right? So the measure is just same for all the entries. So the discrepancy is small. That means actually the number of zeros minus number of ones is small. So any rectangle has a roughly equal number of zeros and ones, right? So any monochromatic rectangle, of course, monochromatic means it has all zeros or all ones. This must be small, because the number of zeros minus number of ones is the size of the rectangle, and this must be below the discrepancy, right? If we took the uniform distribution, if you take some other distribution, then of course it will still be small in the sense of it will have a small measure, but we don't know whether it will have a small number of entries, right? It still be small in the sense of mu. According to mu, it will be small. Okay, so this is discrepancy. So again, I think we even saw this bound, just the theorem I stated the theorem last time. So one of the theorems, or the theorem that we are going to show, is that this bounds the the distributional complexity using the discrepancy, right? So consider the discrepancy according to the distribution mu of f. Now this gives you a bound on the distributional complexity of the function based on the discrepancy of the function f, right? Okay, now let's see how the thing is proven. So let P be a protocol where with cost C, where C is the left hand side, that is the distributional complexity, and such that it is correct on at least half plus epsilon fraction of the inputs. Okay. Why we are taking half plus epsilon fraction of the inputs? Because the subscript of the distributional complexity is half minus epsilon, which means it is allowed to make an error on at most half minus epsilon entries, fraction of the entries. So it should be correct on at least half plus epsilon fraction of the inputs. So let P be such a deterministic protocol, right? Of course, there should exist such a protocol because we are picking the cost to be equal to the distributional complexity. Now look at the set of leaves of P, right? And for a particular leaf small l, let RL be the corresponding rectangle, right? So we have the protocol tree, and for each leaf L, we can look at the corresponding rectangle, right? Now, what do we know about the so let's assume that so we know that it is correct on at least half plus epsilon fraction of the inputs, and let's further assume that take a rectangle. Now this we know it's a rectangle in the sense of the protocol, so the protocol is going to output all zeros or all ones. Once you get to that leaf, right? So consider a leaf rectangle. Now the protocol, it's a leaf of the protocol, so the protocol is going to output all zeros or all ones if the protocol reaches that leaf. Now you look at the measure of all the zeros inside the rectangle and measure of all ones. Now it makes no sense if the rectangle contains 60% zeros and the protocol outputs 1, right? Because you can get a better protocol if it is 60% zeros, then it makes more sense for the protocol to output 0, right? So we can assume that the protocol is doing that sensible thing, that is, if most of the entries are 0, then it is going to output 0 for that rectangle, and if most of the entries are 1, then it is going to output 1 for the rectangle, right? So let's assume that the protocol does this sensible thing, and it doesn't hurt at all to make this assumption because we started with the protocol, and such that it is correct on at least half plus epsilon fraction of the inputs, and this will only improve the fraction of the correctness, right? Now let us look at all the possible pairs of all the possible inputs and look at the probability or the measure of the inputs where the protocol gets it right minus the measure of the inputs where the protocol gets it wrong, right? So we know that the protocol gets it right on at least half plus epsilon and gets it wrong on at most half minus epsilon. So the fraction, the difference is at least 2 epsilon, right? That is the first line here. The fraction in which the protocol is right minus the fraction in which the protocol is wrong is at least 2 epsilon. Now let us take the right hand side and simplify and break it down further. Now we can take each leaf of the protocol and see what happens in that leaf, and we can divide the summation, the first line, into a second line by just restricting the the first line into for that particular leaf. For each leaf, what is the probability that the protocol gave the correct answer minus the probability that the protocol gave the wrong answer, right? Now, suppose now we can consider. So, suppose the right answer was zero. Sorry. Now, suppose the protocol marked that rectangle as a zero rectangle, right? So, when once you are restricted to a rectangle, then fxy will be constant for all the rectangle. Sorry, pxy is the protocol output. The protocol output will be same for throughout the rectangle. So now instead of saying pxy equal to fxy and pxy is not equal to fxy, let's say pxy is 0. So we can say fxy is equal to pxy, which is fxy equal to 0. Fxy not equal to pxy is same as fxy equal to 1, right? Now, if the pxy is actually 1 in the rectangle also, it is the same thing, but with the signs flipped. So what we are doing is, okay, there is a small error here. In the last line, it should not be equality, it should be less than or equal to, okay, instead of equality. So I'll make the correction when I share the slides. This part should be less than or equal to. Okay, so the protocol outputs all zeros are all one. So we just replace with whatever is being done. So this is less than or equal to, and we have the absolute value sign. So it takes care of the flipping of the. It takes care of the flipping of the two cases. But what do we have here? The number of 0 entries minus number of 1 entries, or the measure of 0 entries minus measure of 1 entries, is nothing but the discrepancy of f on the rectangle RL with respect to mu. So basically, 2 epsilon is at most the summation over all the leaves of the protocol, the discrepancy of f on the leaves, right? Now let me go to the next slide. So the first inequality is same as what we just showed. 2 epsilon is at most the discrepancy, summation of the discrepancies over all the leaf rectangles. Now, there are L terms in the summation, and each of these L terms is a discrepancy of RL, of f on RL. But this is all upper bounded by the actual discrepancy of the function itself, because it's the maximum over all such rectangles, of all the rectangles, but which is also an upper bound on all the leaf rectangles. So there are L terms, and each term is upper bounded by the discrepancy of the function. So we have L, the number of leaf times the discrepancy, and since the cost of the protocol is C, the number of leaves is at most 2 power C, right? Because any protocol is a binary tree. Thus we have 2 power C times the discrepancy of f. Now if we just rearrange the terms, we get the next line. C is at least log of 2 epsilon divided by the discrepancy. And if you just recall, C was chosen to be the distributional complexity of f with respect to the distribution mu, and the maximum allowed error is half minus epsilon. So if we just replace that, we get the theorem again. Okay, just to recap, we chose a protocol such that it is correct on at least half plus epsilon fraction of the inputs as per mu. You looked at all the leaves, right, of the protocol. Now we assume that for each leaf, the protocol labels it. The protocol labels RL. The protocol labels the leaf with 0 if 0s are greater in measure in that rectangle, and 1 if 1 is greater in measure in that rectangle. Um, so this is so yeah. So I'm just wondering where that is actually used. It seems like I think in the third line, already mentioned that this should be less than or equal to. Perhaps in this line we need that. No, sorry. We don't need that over there. We need it in the second equality because when we write this as a summation of this, we are assuming that we are assuming that um, mm, do we assume anything there?